In Orbit, REXUS BEXUS Edition, our new series of live interviews organized by Team DROPSTAR. If you're familiar with DROPSTAR, you know that our team participates in the REXUS BEXUS Programme, a German-Swedish student program where teams from all over Europe are selected to design, build, and execute an experiment in one of the two available platforms, BEXUS, a stratospheric balloon, or REXUS, a single-stage rocket. In Discussions in Orbit, REXUS BEXUS Edition, we interview fellow REXUS BEXUS teams in order for them to introduce their experiments to the public and share their experience in the program. So today's team is PR4.
Yes, Team PR4 has a goal of developing a two-part payload on the REXUS rocket. The first experiment uses radiometry for live location and orientation tracking of the REXUS rocket during its flight. And the second experiment performs astrophysical measurements by characterizing the flux and arrival direction of cosmic rays using a detector built in CubeSat specifications. Yeah. The experiment provides a unique opportunity to study cosmic rays in a domain between ground-based and space-based detectors. So let's get to know the team behind the experiment. Hello, PR4 team. If you could quickly introduce yourselves to the public.
Hi, everyone. We are the PR4. I'm Dan. I'm the team leader of the team. And I'm a bachelor student in mathematics, physics, and earth sciences. And now my fellow teammates can introduce themselves.
I'm Sam. I study at Radboud University. I study mathematics and astrophysics, and I am the software sub-team lead for PR4.
And my name is Roel. I also study astrophysics at Radboud, and I'm the system engineer.
Great. So let's start with the most basic question. Can you describe us the concept of your experiment? What is the PR4 experiment?
Yeah, we can do that. We have, as you said during the introduction, we have two experiments essentially. The first one is a radio interferometry experiment. We put a transmitter on the rocket that will broadcast a signal. And then we have multiple antennas on the ground. And these antennas on the ground, they will measure the signal from the rocket. And using the difference in phase received between pairs of antennas, we can, we will try to locate the rocket. We can get into more detail if you like, or...
Yes, of course, please, okay. Go on.
Yeah, it would be nice for you to describe what is the science behind your experiment.
Yeah, so the science is basically, it's based on a concept called radio interferometry. And it's a similar concept to the one that the EHT, the Event Horizon Telescope, uses to take the pictures of black holes. So basically what you do is you have a source that's emitting some frequency of electromagnetic waves, and you have multiple receivers. And depending on the orientation of your receivers, the signal from the source is coming in at different times. Now, of course, an electromagnetic wave is a continuous wave, so it repeats after one wavelength. So if you measure the time that a signal comes in, you have some difference between your receivers, and you have a few possible locations for your the point for your source, basically. And of course, because those waves repeat, you get multiple of those, or a whole lot, basically, a whole lot of those solutions. And if you have more receivers and you use the data that you get in a bit of a smart way, then you can rule out a whole lot of those possible locations for your source, and you can very accurately pinpoint where your source should be at that time. And we're using that, of course, to track the rocket. That's most of the time now done using GPS. But GPS is fairly it's fairly slow, actually. Of course, the REXUS Rocket is accelerating really fast, so it goes up, and once the GPS gives you a new location for your rocket, the rocket is already maybe 100 meters further away. So what we're trying to do is use this technique, which should be a lot faster, to track the rocket not once per second, which is what GPS does, but 1,000 times per second. So you get a more accurate location, or more updates of your location. And the idea is also to make it more accurate, so within centimeter scale accuracy.
Yeah, so that's our first experiment. Our second experiment deals with cosmic rays. So we're building a stack of this special material that will light up when it gets hit by a cosmic ray. And if we stack them after each other and we have a look at how many of these plates got hit, then we can see, then we can create some possibilities where this cosmic particle could have come from. So in this way, we can count the cosmic rays, and we can also predict the arrival direction. And this can give us all kind of information. For instance, if these particles follow the Earth's magnetic field, that is one way we can use it. And we are making this in the size, so it would fit in 2 CubeSat units, so that it might be, in the future used on CubeSats to measure cosmic ray arrival direction.
Great. So, we know that managing an experiment on the REXUS rocket is very complicated, let alone managing 2. And you mentioned that you want to use a new and innovative technique. So your experiment as a whole has to be innovative and unique as well. And what are those technical characteristics that make it unique?
I think mostly, as I try to get across, is that the way that location tracking is done now is fairly good. Of course, we're not trying to shit on GPS or anything, but it could be better in certain specific situations, like for instance a rocket launch with very high accelerations, where you want to know the location of your rocket very accurately. The idea is if you can get the location and very accurately and very fast, you could use that for a whole lot of purposes. Of course, that's not what we're doing right now, but if you perfect it, you could use it to maybe steer the rocket, try to prevent some things that you wouldn't be able to prevent using GPS because you're just not fast enough. And the cosmic ray experiment is it's basically the new thing about it is that most of the time when you try to measure cosmic rays, you either measure from the ground using ground-based receivers, which is fairly hard because, of course, cosmic rays, when they hit the atmosphere, they often react with it, and they create a whole lot of new particles that stream out, and you're basically detecting those particles and not the original cosmic rays. Or you can track them from space using a CubeSat, which is maybe a future thing we might do. But right now, using the REXUS rocket, of course, it goes about 80 kilometers high. It's an opportunity to study cosmic rays in an area where they're not studied very frequently, namely basically between the space-based receivers and the ground-based.
I see.
Yeah.
So I guess what most of our audience would like some clarification on is, could you elaborate a bit on the connection between your 2 experiments? So for you to be using a different technique to pinpoint the location of the rocket, there must be some necessity to it. And as we understand, there is a very large difference between the accuracy of GPS and your measurements with interferometry. So could you specify exactly why that is necessary for your experiment?
Yeah, we can share the connection, because for this cosmic ray instrument, it's important to know the orientation of it and the location, and especially the rotation as well, to accurately measure arrival direction. Because if we don't know the orientation of our cosmic ray measurement instrument, then we cannot tell where it came from. Like, we can tell where it came from relative to the instrument, but we don't know where the instrument is, so we still cannot make other conclusions than just counting cosmic rays.
Thank you for that answer.
Yeah, the way we're trying to determine the orientation of the rocket is that there will be 3 separate transmitters on the rocket, which we are aiming to basically track separately. So we know the location of those 3 transmitters. We know the location of all 3 of them, and using that you can say something about the orientation of the rocket. And of course, then we can also say something about the direction the cosmic rays can. Is the idea.
Very, very interesting. And what is the current status of your experiment? What are you working on this period of time?
Yes, so we recently made a visit to Esrin Space Center, where the rocket will be launching, to gather some data about how our receiver stations are functioning, how they hold up in the cold weather there. That has been very interesting, and we are currently working on analyzing the data we gathered there. And with respect to our radiation measurement project, we are working on the mechanical design of the scintillator stack, so the stack of plates that will be measuring the cosmic rays. And what else are we working on?
Well, for the interferometry part, we Sam here actually made some interesting discoveries, because he worked on comparing a few methods of interferometry, because we have different ground stations, and these stations consist of 3 antennas spaced about 1 meter apart. And of course, we can try to calculate the position of the rocket by comparing these pairs of antennas on one ground station. However, he found that the accuracy on this is relatively small and not the standard that we are trying to achieve. So he also found that when we compare the results of antennas between different receiver stations that will be about 1 kilometer apart or so, that we get a lot better results. And one of the problems we are actively working on currently is getting this method where we use different antennas and compare different data sets on different receiver stations with each other to get that to work. So one problem, for instance, that we face in this case is a time synchronization problem, because every receiver station will have its own clock. So these 3 antennas on one receiver station will have the same timestamp. However, when we look at different receiver stations, then we have an uncertainty in the time. And since we are trying to measure signals that go with the speed of light, if we have an uncertainty in time of 20 nanoseconds, already 10 whole waves have passed. So we need to compensate for this. And one of the things we are trying to find out is how we can compensate for this. And also if we can make our algorithm of calculating where it should be more efficient.
Yeah.
I see. Well, it does seem like a really complex experiment, especially since you're combining 2 experiments in one. And it does seem like you need a wide variety of expertise to mount to such a task. So can you tell us more about the team? How many members are there, and how do you organize to tackle this this big task that you're on?
Yes, so our team currently consists of 16 active members. We have divided our team into 5 different sub-teams, and each of our members are dedicated to 1 or 2 of these sub-teams. yeah, like we have a lot of different students with a lot of different backgrounds. So as we already mentioned, mathematics, astrophysics, earth sciences, but also electrical engineering, and many more that I just forget.
Yeah, which is very necessary, I think, because of
Yes.
course for the experiment we need to the science. We need to know the science behind it, like the interferometry part, and how we're gonna make that to work and get actually accurate locations. But of course, we also need to actually build the thing, which isn't as easy as you expect coming into it. So
No.
you need yeah, a very wide variety of people with very different expertise, which is sometimes makes it a little hard to kind of get everything together and get everyone on the same page. It's a nice challenge.
And next to these 16 students, we also have a small group of 4 high school students that we are guiding to do a small part of our project with us.
What
Oh,
we
that's
are still missing is like some people from an academy for arts or something. I would like that a lot. They can do our outreach and like draw cool things and stuff. We are missing artistic people.
Well, good luck on that recruitment.
Yeah.
And I'm gonna take you back in time a bit to the selection workshop. How did you prepare for your selection in the program? Were you anxious? What was going on?
Yeah, we were anxious. So we did a lot of preparations. We were lucky that we have done something similar before. So before this iteration, PR4, we had another iteration called PR3. And with that team, we launched on REXUS 25. And there were some old members of that team that guided us a bit and told us a bit how they did things and what we could expect. And they expected our chances to be relatively okay. So we were happy to hear that. That relieved us a bit. But we prepared with 4 students, which I was one of. And yeah, we were anxious because we thought, well, if we do something wrong during the presentation, then we screwed over the whole team. And it took a few days to get rid of that feeling and to realize that somebody should do it, and we did our best. And if someone else did the presentation, then they also could have screwed up.
And of course, I think now that we're working on it for like what is it, 1.5 years or something, you know the people, you know the people from SSC, from DLR, and you're comfortable with them. Coming into it, you might be a little bit intimidated because they're actually people working in the aerospace industry. Sorry. And you can kind of get the feeling like, oh, if I say one wrong, hound me on it, and you know. But yeah, once you get to know them, and now we're working with them 1.5 years, they're a lot nicer than you.
The space people don't bite.
No.
We also had our fellow student Katerina, and she worked together with me on the selection workshop. For her, it was also really a moment of bonding with us, and it was for her also like the first time she really felt part of the team. So after the selection workshop, after everything was done, after we did the presentation, we like gathered at someone's house to have sushi and wine, etc., and then like have some bonding with each other. Like this, it was it was an interesting period as well because, well, you felt kind of important when you got into a private meeting with like these space agencies and stuff, and you got to give them a presentation. That felt special, but at the same time, yeah, we were a bit anxious. But they don't bite.
It is true that they don't bite, and
We can guarantee that.
we can guarantee we're bite free. But I mean, there are some nerve-wracking moments, as you described. Like the selection workshop is the beginning of everything. You don't know anyone, and you just enter headfirst into this this thing that seems unamountable to your head.
Oh, I remember our selection workshop. It was nerve-wracking to say the least.
Yeah, some people actually couldn't talk there, so
Yeah.
nervous. But as you described, there are beautiful moments, and dare I say, they heavily outweigh all the the stressful moments inside the program. So, could you describe what your experience is so far in the REXUS BEXUS program?
Yeah, our experience has been, I would say, extremely positive. Yeah, we've met a lot of interesting people from the European Space Agency, from SSC, from DLR. Yeah, we've got to learn a lot of things about, for example, how the European Space Agency operates and what their workflow is like. That has been very educational to us. Yeah, would anyone like to add something?
Yeah, I think for a lot of people in our team, but I think most teams that participate in REXUS, working in aerospace and with ESA and yeah, space stuff is kind of a dream. But of course, that makes you run the risk of kind of idealizing. And I think participating in a program like this, it's you get to see what working in aerospace is actually like without the really hard parts. Like it's a bit of it's of course a student version of what they actually do at ESA, and I think it's good to see that before you actually commit to working, making it your dream. Like, do I want to work in here? It's kind of a soft intro into it.
And we went to S-Range. That was fun. They had snow. We didn't have snow this winter in the Netherlands, but in S-Range they had snow.
Lots.
We had lots of fun with the snow.
Yeah, snow is always fun.
It was also a nice moment to bond a bit more with our mentor, because he was there the whole week with us, or the whole like 4 days with us. It was nice to speak to him a bit as well. He has been of great help. He hasn't bitten us yet either. Maybe if he does, we turn into a space person. That would be cool.
So, as you described your experience, we have to remember that we are all participants doing this because we truly believe that our experiments will have a contribution to the science or the technical industry. So, what will be your experiment's contribution?
Well, we of course have 2 experiments. Let's start with the first. If we succeed in proving concept, giving proof of concept for our radio interferometry location system, then that can be applied on rockets. So one of the advantages of using a system like ours on sounding rockets specifically is that because these sounding rockets accelerate really fast, usually with location measurement methods, you cannot really do anything anymore as soon as it launched. However, our system gives the possibility to maybe add a tiny bit of steering, or to like let the rocket explode if it goes in a really wrong direction. It also introduces the possibility to give a second check for location. This is we noticed that this was important when we were talking to another Dutch space company called T- Engineering. They helped us as well with a small launch in the past, and that was a great experience to have as well. Something else this could be used for is in totally different sectors, because we are doing an experiment called Alex as well with the Austrian Space Forum, and there we are trying to use a similar system, or at least a similar methods, to track analog astronauts that are simulating a Mars mission. And on Mars, of course, there is no GPS because there is no GPS constellation there. So it would give a cheap alternative to radar on Earth and a lot cheaper alternative to a GPS constellation on other bodies like Mars. The second experiment we have can give us a lot of information about cosmic rays. This is well, especially in the atmosphere itself or like the lower space, because there's something interesting happening there. Because as Roel described earlier, when a particle comes from space, it breaks up. Usually that's called a shower. And after a while, these particles disappear. Therefore, we found, like in the past, that there is a point in the atmosphere where there is like a biggest number of particles. There are more particles than in space because of this showering effect, but there are also more particles than lower in the atmosphere when they have disappeared. And there are some studies suggesting that cosmic rays have effects on formation of clouds, for instance. So the ability to study these cosmic rays might, well, give a lot of other possibilities for other research. And we are building it on a small scale so that it would fit into a CubeSat to make a network out of it or something. And this arrival direction could also tell us a bit more about the magnetic field. For instance, do cosmic rays follow the magnetic field? And something else that happens with these cosmic rays is that during a solar maximum, when the solar winds are stronger, the cosmic rays behave a bit different. So it would also make it easier to study those effects, especially also the differences between high and lower latitudes. So yeah, we have a lot of applications of our systems.
Right. Well, we certainly do hope that we see your results as we fly alongside each other. And it does look like your experiment has so much to offer. Well, since it's basically two experiments, right? So even if one goes wrong, the other will have some data. And well, since we are mostly through the largest part of the timeline of the REXUS timeline, basically. You've gathered quite a few experiences, and you must have grown a lot as people and as professionals in the sector. So we assume that you would do some things differently if you were to start over. If you were to enter the campaign right now, some things might have been executed in a different manner. So what advice would you give to a team or people starting on the REXUS BEXUS campaign now? And if each one of you could like share his opinion on the matter.
Yeah,
Yes.
of course. So
Yes, well, this might be very specific to our situation, but I would suggest that you don't start as the second iteration of a project, because we've had a lot of trouble with information being passed from the previous iteration to us, and with how the hardware they developed works and how we can use it. Yeah.
Yeah, we
Yes.
basically had to learn a lot about their design before we could start on our part of the design. I would say in the moment when you're designing something or you're planning something that you have to do, it might seem very tedious to start writing it all down, but do it, because we had a lot of trouble, and we still do have a lot of trouble with, because we have a large team. There's a lot of people involved, and getting them all to work on the same project towards the same goal can be very hard if you don't have a lot of documentation about what everyone's doing, especially if some people leave or some people come into the team. You need to kind of get that info across, and I think the best way to do that is just write it down and have some new people have them read it, have them get introduced with the team, and that can be very hard if you neglected to write the documentation for the stuff you're doing at the time.
Also, especially if you're doing something insane like a launch campaign, everyone will be super tired, can't think. It's very helpful to just have everything listed on a spreadsheet.
Something I think is important is to start with a good team structure, because our team was a bit chaotic, and I like that at first, but we didn't get a lot of stuff done. Then a few months ago, we decided, well, we didn't like it anymore, that the way it was, and we came up with a new team structure, and with these sub teams and this like chain of where everyone goes and where we can find the information. And this has been really helpful for our team, and this has been really helpful in receiving, for instance, new people, and it's really got everything going. We now also have 4 members that together, for every question, know either the answer, who of the other 4 knows it, or where to find it. Things like that are also really helpful for us. And that is a lesson that we learned quite late during the campaign, but it was important. Some other lesson that we had is you have to write this student education documentation, and nobody is going to like that. However, however, if you work on it together, it actually isn't that bad. It actually can be a lot of fun. Like I had quite a good time during our S&D day last time, because in the beginning we worked on it individually, and then it's tedious. Like you don't want to do that. You don't want to sit at home writing the SCD. But if we are all here and we like promise some snacks, then at least we have some fun together. It's actually it's kind of fun writing the SCD together. It's not bad. It sounds like overrated, but it's not. Do it together.
And I think the good thing to note, last thing, is that all of the lessons that we listed so far are kind of organizational things, which is, I think, a big part of your contribution in the program. Because of course, most of the design things and like specific knowledge things that you learn, you can also learn at university or from a book or something like that. But a lot of these things are often only taught by actually participating in a program or in an experiment like this.
Valuable piece of advice that we hope that future participants take into account. So PR4 team, this wraps it up for our interview. We want to thank you very much for participating in our series Discussions in Orbit REXUS BEXUS Edition. And we hope and wish you the best for your experiment, and see you in the next REXUS BEXUS campaign.
Thank you. Thank you, guys. Thank you for hosting this. And a quick question for you: How is your progress going? Is it going well? How is the space mayonnaise system getting anywhere? Are the astronauts gonna get like mayonnaise with their fries soon, or do they have to wait?
Well, I think we can say that they will get mayonnaise.
Awesome. That's great to hear.
That was very happy with.
We do hope that they get their mayonnaise. We are running like everybody else at this time because IPR is closing in. But we hope that everything is scheduled. We're working on everything at the same time, and it can be kind of hectic and insane. But it's come to the point where, like each review, you have to stop talking about, oh, that will happen then. No, it has to happen now. And that's the stage that we are at. We hope it can suffice so that we may resume.
Awesome. Well, good luck.
Yeah.
Yes.
Great to hear that.
Thank you very much. And see you on the rocket.
Yeah, see you on the rocket.
Goodbye.
Bye-bye.
Bye-bye.
Bye. Bye.